Today, we are exploring Advent of Code 2023, Day 12, Hot Springs. I'm going to show you 40 lines of code which solve it in 300 milliseconds. Let's dive in. We are given a list of springs arranged into rows. For each row, the condition records show every spring and whether it is operational, dot, or damaged, hash mark. This is the part of the condition records that is itself damaged. For some springs, it is simply unknown, question mark, whether the spring is operational or damaged. After the list of springs for a given row, the size of each continuous group of damaged springs is listed in the order those groups appear in the row. This list always accounts for every damaged spring, and each number is the entire size of its continuous group. That is, groups are always separated by at least one operational spring. 4 hash marks would always be 4, never 2,2. Equipped with this information, it is our job to figure out how many different arrangements of operational and broken springs fit the given criteria in each row and sum those counts. To do this, I first read the input line by line and convert the list of groups to integers. Then I added a functional spring, a dot, at the end of the springs to make sure that there is an operational spring after each damaged group. Then I called arrangement count function and summed all the arrangements. The arrangement count function is a recursive function with argument p representing a position of spring we are currently investigating. G is the number of damaged group we must process next, and argument springs and groups are just the input data. It returns a number of possible arrangements from position P and group G. At the beginning of the recursive function, we must always terminate the recursion. I do so when there are no more groups to process. Beware of an edge case where there are no more groups to process, but there are damaged springs in the rest of the input. It means there is no solution. Therefore, I return 0. Otherwise, I return 1 because I found a valid solution. I also terminate recursion if we run out of springs, but there are still groups to process. If the current spring is labeled with a question mark, I try to place the whole damaged group of springs here. If it is possible, I explore the solutions involving placing the group there and not placing it there. Otherwise, I just explore the solutions not involving placing the group there. Similarly, if the current spring is labeled with a hash mark, I must start the damaged group here. Otherwise, there is no solution and I return to 0. I skipped operational springs. This code tries all possible arrangements and returns their sum. In the second part, we must unfold input, hence make it longer, 5 times longer. It also means we cannot use the simple approach from part 1, or can we? There is this technique called dynamic programming, where an algorithmic problem is first broken down into subproblems. The results are saved, and then the subproblems are optimized to find the overall solution. That is exactly what I did in the first part. So I added 3 lines of code, and voila, I have an efficient DP algorithm. I introduced a memo table which contains the results to the subproblems. When I reach the same subproblem again, I simply look up the result in the memo table. It is as simple as that. We can use the same technique on both parts of this puzzle. The solution is going to look like this. That's all I have for you today. If you have any questions or comments about this, please put them below. If you like this video and would like to see more like it, please subscribe. Thank you.